Hi, I'm Ryan Baker, and this is Big Day in Education. Today we'll start a discussion of prediction models. In prediction modeling, you may recall that the goal of prediction modeling is to develop a model which can infer a single aspect of the data, the predicted variable, from some combination of other aspects of the data, the predictor variables. Sometimes it's used to predict the future, and it's hard to make predictions, especially about the future, as Niels Bohr once said, and sometimes it's used to make inferences about the present. So let's talk about some examples of prediction. Let's say that a student, you, is watching a video in a MOOC right now, me. Are you bored or frustrated? Hopefully not, but we can try to detect that. Let's say that a student's used educational software for the last half hour. How likely is it that she knows the skill on the next problem? Let's say a student's completed 3 years of high school. Can we try to predict what will be her score on the college entrance exam? What can we use this for? Well, a lot of things. First of all, improved educational design. If we know when students get bored, we can improve that content. Second, automated decisions by software. If we know that a student's frustrated, let's offer the student some online help. And third, informing teachers, instructors, and other stakeholders. If we know the student's frustrated, let's tell their teacher. What I'm going to talk about specifically in this lecture is regression in prediction. In regression, there's something you want to predict, the label, and that thing you want to predict, that something, is numerical. Maybe it's the number of hints students request. Maybe it's how long the student takes to answer. Maybe it's how much of the video the student will watch. In this case again today, hopefully all of it. Maybe it's what the student's test score will be. Now, in prediction, a model that predicts a number is called a regressor in data mining. The overall task is called regression. To build a regression model, you obtain a data set where you already know the answer, and that answer we call the training label. For example, if you want to predict the number of hints the student requests, over here to the right, each value of num hints is the training label. Associated with each label are a set of features, other variables, the predictor variables, which you'll try to use to predict the label. So here you see that P-no, time, total actions, and maybe skill as well, are predictor variables. The predicted variable, which you have labels for, is num hints. And you use those labels to try to build a model so that then you can predict the value when you no longer have those labels. The basic idea of regression is to determine which features, in which combination, can predict the numerical label's numerical value. Linear regression is the most classic form of regression, and in fact, many courses don't actually go anywhere past it. An example of that would be num hints equals 0.12 times P-no plus 0.932 times time minus 0.11 times total actions. So in this case, if you try to predict num hints from P-no, time, and total actions, however, it's worth pointing out that these variables are unlikely to be scaled the same. If P-no is a probability, it'll be from 0 to 1. We're actually going to discuss this variable in some more detail later in the class. P-no turns out to be a common way in educational data mining of referring to the probability the student knows the skill. And this task is called latent knowledge estimation. It's a type of regression, but in practice it actually ends up getting treated as its own special case within educational data mining, because it's different than a lot of other problems. And time is a number of seconds to respond. That's going to be from 0 to possibly infinity, although hopefully we're going to cap it if it looks like the student takes 15,000 seconds to respond. Because of this, you can't interpret the weights on these in a straightforward fashion. P-no is inherently going to have much bigger weights than time, so you need to transform them first. A transformation is when you make a new variable by applying some mathematical function to the previous variable. One type of transformation that you might want to use is unitization. It increases the interpretability of the relative strength of features. And it also reduces the interpretability of individual features. It's harder to understand exactly how many seconds is associated with a change in num hints. So it actually makes it a little harder to interpret the individual features, but if you want to compare the features to each other, it's really important. So for unitization, the transformed x is x minus the mean x across all the data points divided by the standard deviation of x. In linear regression only fits linear functions. It's kind of the name, right? But that's not quite the case when you apply transforms to the input variables. You can actually fit very different functions, which most statistics and data mining packages, by the way, can do for you, can help you set up. So for example, let's take the natural log of x. That helps you fit functions that look like this. Or let's take the square root of x. Kind of looks the same, but not quite. And you'll notice it doesn't drop down below 0. X squared. If you transform first, you can get a very nice reverse bell curve out of x squared. X cubed, you know, kind of this function. 1 over x, that. Sine wave, not all that useful, but you can do it. So with linear regression, you can use these kind of transform functions to be able to fit very different functions of linear regression. So it's surprisingly flexible. But even without that, it's also blazing fast, which is good if you got a lot of data. And it's often more accurate than more complex models, particularly once you cross-validate. We'll talk about cross-validation later in the class. And it's feasible to understand your model with a gigantic honking caveat, which is that the second feature in your model is in the context of your first feature, and so on. Let me give an example of that caveat. Let's graph the relationship between the number of graduate students the professor has and the number of papers the lab produces per year. And I should say, by the way, this is completely made-up data. So you see that on the x-axis we have the number of graduate students, on the y-axis we have papers per year. You can see that as you get more grad students, you get more and more productive until there's this kind of point where you're just spending all your time meeting with your graduate students and your productivity actually goes down a little. Or maybe it's too much time spent filling out personal action forms, which I spend far too much of my time doing. Let's look at the model. The model is 4 plus 2 times the number of grad students minus 0.1 times the number of grad students squared. You might look at this and the easy interpretation is, well, the number of graduate students squared is associated with less publications. But that's actually not true. In fact, the number of graduate students squared is actually positively correlated with publications. It's a correlation of 0.46. We'll talk about correlation in a bit, but it's actually a positive relationship between grad students squared and publications. It's only in the negative direction when the number of graduate students is already in the model. So in other words, even in this incredibly simple case, you can't just straightforwardly say, okay, plus sign for number of graduate students, minus sign for number of graduate students squared. You have to think about what the whole model means. So be careful when interpreting linear regression models, or really any other kind of model just about. There are other kinds of regression beyond linear regression. There's regression trees. I tend to like that. There's nonlinear regression trees where, for example, if x is greater than 3, y is 2. But if x is less than negative 7, y is 4, else y is 3. This can capture nonlinear relationships. There's another type of linear regression trees, M5 prime, where you actually have linear equations at each of the leaves of the tree. So if x is greater than 3, y is 2a plus 3b. But if x is less than negative 7, y is 2a minus 3b, and so on. And what this allows you to do is to say that there are different linear relationships between some variables depending on other variables. And for example, if you had a linear regression tree, you could fit this as an M5 prime tree and say it goes up linearly up until 6 graduate students, then it's flat through 13, and then it goes down again after 13. This may not perfectly capture your data, but it may actually be a clean way to describe the data. In later lectures, I'm going to talk about other regression algorithms. I'm going to talk about goodness metrics for comparing regressors, and I'll talk about how to validate regressors. In the next lecture, though, I'm going to kind of quickly start to overview classifiers, which are another type of prediction model. So thank you very much for coming. I hope you found it interesting. Post in the discussion forum. Discuss. Thank you very much for coming. I'm Ryan Baker. This is Big Day in Education.